All right, so I think the group yesterday too, we looked at the first two examples here, and the force diagrams are actually identical. We have gravity pulling the object into the ground, and we want to think of the ground as responding like a spring would with a certain amount of normal force. There's no acceleration here, and so the net force is 0. Somewhat surprising at first, perhaps, is that number 2 is the exact same force diagram. Again, gravity would be pulling this object into the ground. The ground responds with a force, normal force we call it. Again, here normal means perpendicular. A normal angle is a 90-degree angle. So when we think of normal force, think of, I really wish I could rewrite the physics books and call it a perpendicular surface force, because that's really what it is, but that's a mouthful. So when we, again, I want you to think of normal force as this active thing that comes from a compressed surface. The temptation, I think, is to put an arrow in the direction of motion. We can't have that because an arrow, a force in the direction of motion, would require that the object is speeding up, accelerating, okay? So at some point in the past, yes, this thing was accelerated, and then it would just slide without friction at a steady speed because of inertia. It's not going to speed up, not going to slow down. So again, our net force is 0. All right, number 3. So if the object then encounters some friction, so maybe it goes from a frictionless surface to a surface with some friction, it will slow down, which means it has a force opposing its motion now. And I've labeled that with FKF for kinetic friction. So kinetic friction is opposing the motion. The net force would be to the left, and if something is moving to the right but encountering a net force to the left, it's going to slow down. So one thing that we'll kind of learn going forward is that the direction of the net force, so the direction of any unbalanced force, will also be the direction of the acceleration. So if this is moving with a velocity to the right but slowing down, the acceleration is to the left, and it's the net force that's causing that. All right, any questions on 3? Right. So number 4, very similar to the first problem, except instead of being on a surface, the object is hanging from some sort of rope or string or something like that. So the only difference is the upward force. It's not a normal force because it's not from a compressed surface. We call it Ft for tension force. And again, the way we think about it, a tension force is kind of an active process. This string or cable would be getting stretched, and just like a spring that's stretched, it would exert some force back. So it's not that the rope or cable knows exactly how much force to exert. It just stretches to a stretch amount that will balance gravity. So net force of 0, again, acceleration 0, net force 0. All right, number 5, object pulled upward at constant speed. So there's a force here exerted on the string. That's going to cause some stretching in the string or cable, whatever it happens to be. So it's a tension force, again, upward. The key here is constant speed, which means 0 acceleration. And so the temptation might be to have a bigger upward force. If the tension force was bigger, we would actually be accelerating the box upward, okay? So at some point in the past, to get this thing moving, yes, there had to be more tension force to accelerate it. But if you wanted to just continue to raise it at steady speed, a balanced tension force would be enough to do that. And again, that's the concept of inertia. Once it gets moving, it's going to continue moving at a steady rate, even if the forces are balanced, okay? And maybe you've experienced that. If you have to pick something up that's heavy, to get it moving, you do have to exert a pretty big upward force. But once it has some upward inertia, you don't have to exert as much force to keep it moving. All right, object pulled by a string and speeds up. So I know the acceleration is going to be to the right, which means I need to have a net force to the right. Since it was a string, I called it a tension force. It doesn't say specifically whether there's friction or not. If there was, and you want to include kinetic friction, you would include a smaller amount of kinetic friction as opposed to the tension force. And again, gravity is pulling the box into the surface is pushing back with a normal force, a perpendicular force. So in the up-down direction, everything's balanced. In the left-right direction, we have an unbalanced force to the right. All right, any questions on that first page? All right, number 7. Object is falling and accelerating. We know that gravity causes acceleration. The net force has to be downward. If you wanted to include some air resistance, you could. Air resistance would be caused by the bottom side of this colliding with air molecules. It hits those air molecules. The molecules exert a force. If you included it, you would just need to make sure that the air resistance vector is smaller than the gravitational force vector. And after any bit of falling and speeding up, we would start to probably notice some air resistance pushing upward. If this thing was dropped from a very, very high height, it might encounter more and more air resistance as it falls and speeds up to a point where air resistance and gravity are balanced. Put a little hash mark there. That's the concept of terminal velocity. So it's not that gravity is no longer acting on it, it's that gravity gets canceled out by an upward air resistance if something moves fast enough. And air resistance gets bigger with speed, right? So, think about just swishing your hand through the air. You might kind of feel the air. If you stick your hand out of a car that's going 50 miles per hour, you feel that air resistance. Air resistance gets bigger with speed because your hand, or whatever it is encountering more air molecules that are applying a resisting force on the object. So if we were to kind of play 7 and 8 like a movie, you would see a steadily increasing air resistance vector as the object falls and speeds up. And then as soon as you reach that equilibrium, it still falls, probably at a high rate of speed. It's just not speeding up anymore. All right, number 9 is very similar to the one on the previous page. It just doesn't have a pulley involved. If I want to accelerate the object upward, I need a bigger tension force than gravitational force. Upward net force, upward acceleration. So number 10, it's moving upwards, but slowing down. Gravity is going to be pulling it downward. We would expect that gravitational force to be downward. So the velocity vector would be upward, but the acceleration vector would be downward. There's a temptation here to put an upward force vector. There is no upward force vector, okay? At some point in the past, to get this thing launched, yes, there was an upward force on the object, bigger than gravity, accelerating it upward. But once it launches into the air, you don't need to have force to keep it moving upward. Its own inertia will keep it moving upward. If there was no gravitational pull and you launch something up in the air, it would just go upward at a steady speed, right? It would coast like the hover disk did because there wouldn't be any force downward to keep it from changing its motion. So by putting gravity into the picture, all we're doing is slowing it down, net force downward. If I wanted to include air resistance here, it would also be pointing downward because the top edge now is encountering more air molecules, and we could have 2 downward forces. That would just cause it to slow down even more rapidly. Right. Any questions on 10? Good. All right, so 11 and 12 have to do with friction. We will do a study of friction and get into the details about this. But if you have some object that's heavy interacting with the surface, sometimes you might push it and it won't move, okay? The friction is kind of due to those surfaces being kind of locked together on a microscopic scale. And we call that static friction. So I've got SF. If I'm pushing to the right, my push is to the right. My static friction is balancing it. It's not accelerating. Static friction responds to the push, okay? In the same way normal force kind of responds to the push. And again, we'll talk more details about static friction versus kinetic friction pretty soon, probably a couple weeks from now. So 0 net force because there's 0 acceleration. The difference for number 12 is it's moving at steady speed, so the similarity is that the acceleration is 0. We would have to assume that the pushing force is balanced now by kinetic friction, resulting in 0 net force and 0 acceleration. Again, in the up-down direction, gravity would be compressing it into the surface. The surface would be pushing back with a perpendicular normal force. Okay. Any questions? All right, let me go ahead and stop the recording.